All right, let's try having this conversation about whether there's a better way to do line integrals or not.
Okay.
Okay, so here's the idea. Say you wanted to, in Calc 1, integrate from a to b something that looked like f prime of x dx.
Yeah.
What would you do?
Antiderivative f.
Okay, so what's the antiderivative of f prime?
Fx.
F, right?
So f of b minus f of a.
Okay, so you do f of b minus f of a, right?
Which.
Okay, so let's Calc 3 this up. Right?
Okay.
What's the Calc 3 analog? I want to integrate over some curve.
Yeah.
What's the derivative analog?
Well, dr wasn't. Oh, no.
So dr is the derivative of a path, right?
Yeah.
What's the derivative of a function look like?
There's two directions.
There's two directions, so I need to record a couple pieces of information, right? I need a vector. So I'd write down the gradient. So if I happen to be integrating a gradient, dr, right, then what should I get? Well, Calc 1 would kind of suggest, right? If you're integrating the derivative of something, you ought to get the something, right? So you get what?
F of.
Well, I don't really have ends for c, right?
Yeah.
So if c is a path from a point A to a point B, then what do you expect to get?
F of a b.
You expect to get f at the kind of end you go to minus f at the beginning. You see that? This thing is called the fundamental theorem of line integrals. So this is the fundamental theorem of line integrals. And this is motivated by this example we were doing where it didn't seem like it mattered which path we went along for this vector field, right? And then I started writing down derivatives and you guys were like, hey, what the heck? Why would you think of that?
Yeah.
That's why I would think of it. I wonder, right? Hey, maybe gradient of that, or maybe this vector field that I had, minus y sine x, comma cosine x. Hey, maybe that's the gradient of some jazz, right? If it's the gradient of something, that would mean the partial with respect to x of f is the x component, and the partial of f with respect to y is the y component. So can I exhibit a function of x and y that has these two partials?
So this f is the gradient of some other function.
Yeah, I'm wondering, right? Hey, here's a derivative, maybe. Does it have an antiderivative? Of course, that process is more complicated because I'm in 3 dimensions instead of 1, right? But does it? You guys see a function that has this is the x partial and this is the y partial?
Yeah. Wait, I'm not sure.
Okay, so I'm not sure. Let's try. If I've got the partial of f with respect to y is cosine x.
Well, that's the same as 1 times sine x.
Sine.
Couldn't I just integrate both sides of this dy?
Yeah.
You see that? If I toss one of these guys dy and one of these guys dy,
Yeah, then you just get y cosine x.
then I should get like maybe f. I'm putting approximately equals to because this is a little weird, right?
Yeah, it is.
Is what? Y cosine x
Yeah.
plus
Plus some constant.
some constant, but it has to be constant with respect to
To the curve.
yeah, constant with respect to y, right?
Okay.
Which means it could be a function of x's. You guys see that?
Yeah.
So then I might wonder, hey, is y cosine x, is that thing's x derivative the x derivative I had over here?
Yeah. Yeah.
Yeah, check. Awesome, right? So I found out that f was the gradient of something, right? So before we wanted to do this thing where we were trying to do, right, and here's kind of my example. I was trying to do the antiderivative over some path C of that thing, minus y sine x, comma cosine x, dotted with dr, right? And C went from 0, 0 to 2, 4 along some parabola, right? But I don't give a flip what path it goes along, right? Okay, see that? I just couldn't care less. Because what I'm going to do is I'm going to say, hey, by the fundamental theorem of line integrals, this is this thing, right? Oops, not that thing, but this thing's a gradient. So I find its antiderivative, right? The thing it's gradient of is y cosine x.
Would you find the antiderivative of the partial for each one?
Yeah, and then try to get them to work together.
Okay.
In this case, it was pretty easy because this one worked.
But then would you also have like two separate ones where you...
Yeah, you might have two that you kind of need to finagle.
Like one from 0 to 2 and one from 0 to 4 as well.
Oh, no, there'll just be one.
Okay.
It's got to be one function both pieces work for.
Okay.
So I got y cosine x evaluated from where?
0 to...
From the points.
Oh, from 0, 0 to 2.
From the points, perfect. From 0, 0 to
2, 4.
2, 4. And so I get 4 cosine 2 minus 0. Check, done. Right? Does that kind of make sense? This thing doesn't care which path you go along, because the fundamental theorem of line integrals applies to it.
Okay.
Does that make sense?